Hi, my name is Elizabeth Ramos, and today we're going to be going over writing a molecular formula, the complete ionic, and then the net ionic equations. So we're going to start off with this problem. It says aqueous lead 2 nitrate reacts with aqueous potassium sulfate, and we're going to go ahead and we're going to write out the reactants, write out the products, find out which one's going to be a solid, and then do our complete ionic and then our net ionic. So first, let's go ahead and write them out. So lead is Pb, and it tells us the charge. So it's going to be Pb 2 plus, and we have nitrate, which is NO3 minus. When you put those two together, in order to balance out the charges, here I have one negative and two positives. So I need two negatives to balance out the two positives to make it neutral. So that means it's going to look kind of like this. Then I have NO3 and two of those. So this 2 outside correlates to the entire molecule, meaning there's now a total -2 charge here and a +2, making it neutral. And it says it's aqueous, so we have to make sure to write out that phase state. Next, we have potassium sulfate. So potassium is K+, sulfate is SO4, 2 minus. So it kind of goes with the same scheme, right? So we have, except opposites. We have +1 here and then -2 over here. So in order to balance that out, I need two positives to cancel out that 2 negative. So it's going to look like K2SO4. So now the overall charge over here of -2 is balanced out by the overall charge of +2 over here. And this also says that it's aqueous. Now, to create our products, we're going to see that this is a double replacement reaction. What that means is that our elements, the cation is going to go with the anion of the other and vice versa. So I like to think of it as like just switching partners. So this guy is going to go with this one, and then these two are going to go together. Now, the subscripts, even though they're there, they do not carry over into the products. Instead, we're going to keep their original charges and balance out the molecules like that. So first we see potassium and nitrate. Notice it's +1, -1, so it's just going to be one of each. Even though we have subscripts over here, those do not carry over because those are just to balance out the charges of who they're paired with at the moment. So we're going to keep it like that. When you look at your solubility rules, you'll see that group 1 elements and nitrates are always going to be soluble, so this will be aqueous. Soluble just means that they're going to break down into their ions in water, okay? And then we're going to have lead 2 sulfate. So if we see that's +2, -2, the same thing happens, the charges cancel out, so I only need one of each. And when you look at your solubility rules, you'll see that this creates a precipitate. Precipitate just means that it's going to form like a solid in the solution that's visible, all right? It's either going to be a different color, or it's going to be like chunky or milky or anything that's not clear, all right? So now that we have this written out, we can go ahead and balance it. So we're just going to do that basically in our heads real quick. So over here, I have one lead, so that's balanced. I have 2 nitrates, 1 nitrate, so I'm going to put a 2 out here. Luckily, that also fixes this problem over here. So we have 2 potassiums and we have 1 sulfate. Our equation is balanced, okay? So now this is your molecular formula, okay? This is your molecular balanced formula. Now we're going to go ahead and do our complete ionic equation. So Ci just means complete ionic. And what's going to happen now is that everything is going to break down into its ions if it's aqueous. What that means is that this solid guy is going to stay solid and not break down because, like I said earlier, a precipitate stays solid in solution. This is the most accurate representation as to what's happening in your beaker or in your cup or whatever you're using in terms of ions. So here we have, there's 4 things that I always remember to write down when I'm doing my complete ionic. And that's going to be the coefficient, the actual element, the charge of the element, or of the ion I should say, and then the phase state. Those 4 things you absolutely need, and if you're taking a test, you get a point off. So remember those 4 things, okay? So here I have 1 lead, so 1. I'm not going to write the 1 because that's redundant. So it's 1 Pb, the charge is 2 plus, and it's aqueous. Alright, and then we also have our nitrate. However, let me rewrite this so you can see it better. Alright, and then we also have our nitrate. However, here you see that we have 2 of them. Instead of keeping it on the outside of it, we're going to bring it out to the front as a coefficient so that we can denote that there are 2 of them. So we have 2 NO3, the charge is minus, and it's aqueous. So this is a perfect example of the 4 things that I was talking about earlier. So we have the coefficient, the element or ion, I should say, the ion, the charge of the ion, and then the phase state. So you need those 4 things for each and every one of them. So now we have 2 potassium plus aqueous, and we have 1 sulfate, so SO4, 2 minus aqueous. Our little arrow. These break down 2 because they're aqueous, so 2 K plus aqueous, and then 2 nitrates as well. And like I said earlier, our solid is just going to stay a solid because it's not aqueous in a solution. Alright, so this is a place where you can double check to make sure that you balanced everything as well, because there should be the same amount of ions on both sides at this point as well. So here we have 1 and 1, 2 and 2, 2 and 2, 1 and 1, so we can make sure that we definitely balanced that correctly. Now, for your net ionic equation, so I'm going to put Ni for this one. So when you have a net of something, that just means you're getting rid of things that are going to be the same on both sides. These are called spectator ions. So if you think about going to a sporting event, right, you go to the game, and you leave the game, and you didn't really do anything. You weren't playing, you didn't score a touchdown, even though you might feel like you did. You were just spectating. Alright, so you came and left the same. So if they're the same on the left and the same on the right, then they're going to cancel out, becoming spectator ions. I'm not going to cancel them out just because I want you guys to be able to see clearly what I'm doing, but I will underline them in a different color. So here, I see Pb plus 2 aqueous. I have to look for that exact ion on the other side, if not they don't cancel. So I go over here and I scan through, and even though Pb is here, it's not an ion, so that does not cancel. So that's not a spectator ion. So I'm going to move on to nitrate. I have 2 NO3 minus aqueous. I go over here and I see that guy right here, so he's going to be a spectator ion. So potassium, we're going to do the same thing. We see that he has an exact pair, so he's also a spectator ion. Sulfate is not the same on this side, so he gets to stay there. So for your net ionic equation, everything that's not a spectator ion can come down as well. So as you can see, we have Pb plus 2, or 2 plus, aqueous. This guy is a spectator ion, so he doesn't count. This guy doesn't count either, but this guy does, so plus SO4, 2 minus, aqueous, yields, and then again, these are spectator ions, they do not come down, so it's just going to be our solid. Alright, so that's how you do the net ionic equation. This is a really good way to also double check to make sure that you canceled all your spectator ions. Usually, or pretty much always, it's going to equal your precipitate. So if you have anything extra over here that's not in your precipitate, then I would go back and double check to make sure that one didn't have a partner on the other side or something along those lines. So here we can see that Pb and SO4 is Pb and SO4. So we know that these ions make up this precipitate. And that's a good way to double check your answer at the end. So that is how you do your molecular equation, your complete ionic, and your net ionic equation.